Hi, my name is ZOHARI. My matrix number is EN220106. So now I will explain about the introduction. The most fundamental function of a computer is the fetch-execute cycle, the special set of instructions that the CPU is intended to carry out is known as the instruction set. Instructions are retrieved and carried out from the main memory. The stages of fetch-execute are broken into three parts, which is fetch, decode, and execute. Fetch is one of the main stages of the fetch-execute cycle. The program counter is stored in one register, and then the memory address of the next instruction to be fetched from the main memory is stored in the computer. The data acquired during the fetch step is copied into the instruction register, and at the end of the fetch stage, the first instruction has been fetched. Decode is one of the important part which is necessary to deduce the instruction. It is sent to the control unit through a data bus separated into two halves, opcode and operand. For execute, memory is required for data processing after the decoding has been completed.
An SR-less employing NOR gates is a crucial building block in digital electronics, serving as a fundamental memory unit that can store a single bit of information. In this circuit, two NOR gates are strategically interconnected to create a stable bistable circuit. As you can see, the latch has two inputs, set S and reset R, and two outputs, Q and its complement Q. The circuit operates based on the logic and feedback mechanism inherent in NOR gates. The behavior of the SR latch is contingent on the input S and R. When it says reset R, it means the output Q is equal to 0. When it says set S, it means the output Q is equal to 1. Importantly, if both S and R are inactive, the NOR gates maintain the latch previous state and Q retain their current values, representing the latch ability to hold information. So this is the coding for register using Verilog, and also the result that we got based on the coding. To create a register using Verilog, we can utilize the rect data type, which is commonly used to store logic values in procedural blocks. In Verilog, a register file is essentially a collection of registers that can be both read from and written to by a digital circuit. This concept is a fundamental building block in various digital designs, such as microprocessors and digital signal processors. A register file is typically implemented as an array of registers, where each register is a collection of storage elements. To define a register in Verilog, we can use the rect data type followed by the size of the register.
For create ALU, the code provides a basic implementation of a MIPS processor, ALU, and a corresponding test bench. The ALU takes in two 32 bits input A and B, as well as scan operation code OP and output the result. The test bench provides a clock signal and initializes the input to test the ALU functionality. The test bench uses an EP wave signal to drive the clock and includes a few test cases to verify the ALU behavior. For create state elements on the data part, the test bench and design code demonstrate a 4-bit statement element that can store and retrieve value based on the input clock and the write enable signal. The test bench code sets the clock and test states, and the design code implement a register array to store values. When write enable is high, the state in value is stored in the memory array at the specific address. The value at the address is then passed to the output Q. The test bench code creates a dump file EP-wave VCD to capture the waveform of the simulation.
Hi, my name is ZOHARI and my matrix number is EN220106. So now I will explain about the create data memory unit. So the coding that we use is stated in the slide. And from the result that we get, we can conclude that the X in data out and data in signal lines implies that there are times when the data is not valid or unknown. The transition from 0 to 1 or vice versa represent the binary state changes that occur over time, with the timeline marked in nanoseconds at the top. From the waveform, we can infer that this is a timing diagram showing how data is read from or written to a specific address. The WR signal likely indicates whether the operation is a write or read. The data appears valid at certain intervals, synchronized with the WR signals.
In the test bench stimulus process, the value are assigned to be TB_SE_in input signal, and a designated waiting period ensues before initiating another change in value, with these assigned values being binary representation of hexadecimal numbers, specifically 7FFF and 800 and FFFF, and the TB_SE_out output signal linked to the sign extender component output facilitates the observation of the component's response to the input stimuli. To signify the conclusion of the simulation, an assert false statement is employed, accompanied by a report label N and a severity level of failure. Upon execution of this statement, the simulation terminates, displaying a message label N with a severity level of failure.
For the marks or multiplexer, this is the coding and also the result that we got. A multiplexer or MUX is a combinational circuit that connects any one input line to a single output line based on its controlled input signal. It is used to control the flow of information in digital circuits and is commonly found in microprocessor and digital signal processors. The provided Verilog code is a test bench for a multiplexer MUX module. It begins by declaring the test bench module MUX_TV and defines several register and wires. The MUX module MUX_example is instantiated with the specified inputs and outputs. Inside the initial block, a monitor is set up to display the values of cell I3, I2, I1, I0, and also Y. The input values are then set and the cell value is randomized in a loop. After a delay, the simulation data is dumped into a VCD file for further analysis.
The graph depicts the API waveform for the MIPS Verilog program, showcasing various procedures for executing the complete MIPS data path. A test bench Verilog code is generated to act as the highest level code, providing inputs to the design code, encompassing SR latch register, ALU, states element and the data path, and data memory unit, sign extension unit, and MIPS. The test bench code is initially implemented utilizing a single cycle for each instruction. However, due to its significant slowness compared to a multi-cycle system, a jump code is implemented at the code's end, and the fetch execute process, constituting the basic operational cycle of CPU, involve elements like instruction memory, program counter, and addition for instruction storage and PC incrementation. For this discussion in this project, we create the waveform for digital circuit using the EDA Playground platform. User may edit, simulate, analysis, and synthesis, and share their hardware description language code with EDA Playground, a free online application. By facilitating faster code exchange and easier access to simulation tools and instruments, it seeks to support the learning process of design and test bench development. It is important to remember that EDA Playground is primarily meant for modest prototypes and demos and is not appropriate for large-scale FPGA or ASIC design project. First, to generate the intended output waveform from an SR latch. The coding was developed and an SR latch doesn't require any extra control signals to function. It just depends on the status of its S and R inputs. It may be built with NAND gates instead of 2 NOR gates and a cross-connected feedback loop. However, the latter requires switching and inverting the inputs.
For the conclusion, million instructions per second, or known as MIPS, is a useful metric for quantifying the computational speed of a processor by measuring how many millions of instructions it can process in 1 second. MIPS is a measure of the raw speed of the central processing unit, CPU. The fetch-execute cycle, which involves fetching an instruction from memory, decoding it and executing it, and then storing the result, is fundamental to the operation in CPU. When assessing the performance of the cycle, MIPS offer millions of these cycles a CPU can perform in a second.